Hi, and welcome everyone. Thank you so much for joining the webinar about cellular ambient IoT. I see that people are slowly joining the webinar, so welcome all. Before we start introducing all the speakers for today, I would love to welcome you to share a message in the chat so we know that we're actually talking to real people. And would love to hear as well if you have any experience with ambient IoT, with energy harvesting, with solar panels or whatnot. So feel free to drop them in the chat, and then we start with some introductions. We're going to slowly start giving people some time to join in, and the actual presentation will start, let's say, in 2 minutes or so. Yeah. Before we actually start, let's go and introduce the speakers. So I'll have to go from right to left. So starting with Imad, would you like to say a few words about who you are?
So hello everyone and welcome to this webinar. So I'm Imad Mikhail, I'm product marketing at Sequans Communications.
Hi everyone, Bruno from EPs. I am the Ecosystem and Partners Director, specialized in energy harvesting, and very happy to see you all joining us.
Hi, I am Dan from DPTechnics. We're an IoT development company and IoT building block supplier. So joining in the webinar from Belgium. Welcome to all of you.
All right, thank you all for joining. So my name is Lawrence. I was invited to moderate this webinar, which I'm happy to do so. So I'll take 1 minute to share who I am and what I'm from what company, and then we'll officially kick off this webinar. So my name is Lawrence. I'm from IoT Stars, and IoT Stars is a community of IoT professionals, and we try to share knowledge at exclusive events. Most of the time in-person events, but we also try to facilitate webinars and online events like this. So we have our big next event coming up in November at Electronica, so make sure to check it out. More information can all be found on our website. Then, without further ado, cellular ambient IoT for smarter monitoring, the state of the technology. Ambient IoT goes by many names. I think energy harvesting is maybe the more common ones. So we'll dive into this topic, and we have a few topics that we're going to cover. Starting with some introductions, we have a very cool use case that Dan will share with us. Imad is going to share some information about their solutions from Sequans. We're going to dive in some challenges, and we're going to take a closer look at the Walter module, which is a small, pretty cool hardware module, as well as the EP's solution for energy harvesting. And it starts with the most interesting part, in my opinion, how to start building yourself. So we try to keep it within 45 minutes, more or less. Well, let's see how far we get. Thank you so much for joining. And yeah, I would like to give the word to Dan to kick off his session about livestock monitoring.
Thank you, Lawrence. So yes, energy harvesting is something we have been looking in for quite some time, but it's really in the last few years that more and more the technology has come to a state that it's really usable these days. And with our Walter module and with the EP's chips, you can really build a technology that enables both really low power use cases, but also the really difficult use cases where low intervals and high uplink is needed to do the use case. So maybe go to the next slide. It's something that we have built using our Walter module, and on the Walter module you find the Sequans modem. So that's something that Imad from Sequans is going to dive into a bit deeper.
Thank you, Dan. Quickly, we are starting with the cellular module because it's one of the biggest, or let's say the element which is using the most power in the device, especially when it's transmitting. So who we Sequans, for those who don't, we are a chipset and module maker based in Paris. We have been here in the markets. We have been established in 2003, and we are listed in the New York Stock Exchange. Our business is essentially based on 3GPP kind of technologies, meaning, and this is where you see the Monarch, Calliope, and Taurus, which are three different flavors of the cellular chipsets and modules for the IoT market. But also we have an RF chip, which is called Iris, which is a dedicated RF for SDR applications, software-defined radio. But also Sequans is doing some IPN services, meaning tailored engineering for some specific demand in the market. Following slide, please. So to give you more about the chipsets I have presented earlier, how to read this slide? Well, actually, I mean, within the market, most of the time when we talk about a cellular technology, about 4G, 5G, and even when we used to talk about 3G, it's a kind of, we look at it as a big basket with everything inside, and that's it, something like the technology that's 4G, 5G, etc. While if we zoom in, we see that most of the time when we deploy a new technology, for instance, the 5G, most of the time the deployments start with the technology for the phones, meaning how much throughput can we get out of this technology, for instance, the 5G. However, for the IoT market, sometimes it comes later. Typically, if we look at, again, the 3GPP view, we see some flavors like 5G red cap and 5G red cap. So if I map this to Sequans chipsets, I see in the bottom what I called Monarch, which is a cellular technology dedicated for LTE-M and narrowband IoT. So as you can see, it crosses from 4G to 5G because it's part of the 5G and it's continuing. And on top of it, the Calliope, it is a Cat1 bis today, and the work is ongoing to make it become an eRedCap compatible, meaning when the eRedCap is deployed in the market. And of course, we have the Taurus family and the Taurus Lite, which is a kind of category 3 to category 6 in the 4G area, equivalent or to RedCap, standard RedCap. And again, why don't we have one single chip that can do everything like we used to do in the 2G or 3G? Well, for a simple reason that, as you can see, there are various kind of applications needing those cellular devices, and each one of them has its particularity on how much cost does it have, but also the power consumption. So here, what Dan mentioned is the Walter is based on the Monarch family, which is the lowest one. And indeed, it's one of the lowest power consuming in the market today as a solution for the cellular. Next slide, please. So for the challenge to have a device which can work without replacement of batteries, etc., there are actually two things that we need to focus on to make sure that those conditions are met. The first one is how much energy do we have when the device is awake? So indeed, we need to have sufficient energy to have the module capable of booting correctly, of course, making sure that it can connect to the network, making sure that from end to end it can have enough energy to establish the connection to the complete connection to the network, to do the transmission of the data to the network, and of course to be capable of absorbing the variation of power peaks caused by multiple things that can happen in the field. So this is the working time. But also, we need to make sure that when the device is not transmitting, it is not consuming power uselessly by doing different things. So indeed, it can be in one of the different modes which are known for the idle, let's say, which can be either switched off, or PSM, power switch mode, or EDRX, which each one of them have its different variation. So the application need to make sure that it is in a mode where it's not using uselessly the battery or the available energy when it's not in use. Next slide, please. Thank you. Here I'm zooming in on some key data to give you some key figures on what are we talking about in terms of energy needed for this Cat-M transmission with the Monarch sequence module. So as you can see, of course, I mean, the module is capable of working very down to 2.2 volt and up to 5.5 volt. Well, indeed, I mean, the fact that it's going down to 2.25 volt, it will help you, I mean, it will help us working on very low available voltage. However, here what I'm showing is the instant peak, and the instant peak, I'm not talking about the average, but it's really something that can happen instantly. It depends on a lot of things. We need to keep in mind that we have the power amplifier, which is used to transmit the data. And this power amplifier can cause those peak powers. And as you can see, those peak powers are depending on the voltage, but also on the temperature, which is of the system, which can go between -40 and +85 degrees Celsius. And as you can see, indeed, it's an extreme case, but on a 2.2 volt at 85 degrees Celsius, we can hit 700, we need to sustain 700 milliamp current. But also on the idle, I'm giving some key figures. I'm going to be quick. I mean, the most important one is the 1 microamp, which is the sleep mode of the device. But as you can see, I mean, we have, it depends on the different configurations. I mean, on the typical PSM, with an aggressive cycle of, with an aggressive cycle, it can go down to 48 microamp. And of course, I mean, one important information is about the data transmission. The data transmission, if we take typically a 2 kilobyte on HTTPS, mobile originated at an average condition, let's say, it requires 88 microamp hour. So those are really just to give the expectation, I mean, what is needed in terms of energy to make at least the module be capable of working correctly and having enough energy to be able to boot, transmit, etc., etc. Next slide, please. So all the numbers I have shared previously are coming out from testing happening in lab, etc., meaning we are under a controlled environment, and we have our numbers to characterize the device, and we know what we are needing. But what happened really in the field, because we don't control the field, and the field have multiple variation that can that won't allow us to be in the best environment. So in transmission, the channel can vary by itself, even if the device is fixed. I mean, we are not moving, but the channel is always moving. So we have to make sure that we are we are facing this change. And there are some mechanisms within the network which are the adaptation of the power, etc., by itself, I mean, to make the device work. So we have to take it into consideration. But also we have to keep in mind, again, I mean, all this is in transmission mode, that if the device is not in a good coverage mode, and since we are talking about Cat-M, we have the repetition which can start to happen. And repetition means messages will be longer than expected, because the transmission is getting repeated and repeated until the device is, I mean, make sure the message is transmitted. So those things have to be taken into account. And also in sleep mode, there are, I mean, if we take the look from the sleep mode side, we don't always get what we want. Meaning it depends on the network configuration, which can be configured. I mean, each network can be configured differently. The SIM card that is embarked on the device can have its own impact, because not all SIM cards have same configuration. So you can have different behaviors on the field depending on the SIM card that you have. But also we have to take into account if the device is local or roaming, because in some roaming conditions, the eDRX or PSM are not supported. So meaning if we made something to rely on those technologies, they may simply not work. And of course, I mean, the eDRX setting, we have some requests, not always it's been taken into account by the network. And also the famous one, which is the tracking area update, which is an information that comes from the network. I mean, there is a timer, the 3412, that we can set it from the mobile, etc. But the network is not always taking this into account, and it can even override it and make it shorter, meaning it will require more energy more and more. So in conclusion, what can we take out all of this? In transmission, we need to make sure that we have enough energy to sustain the worst case scenario. I mean, we take all the elements that have been showing, and we can imagine that we are in a very bad condition, very far from the E node B, etc., etc., and we need to cover this case. So we need to have sufficient energy to cover this case. And in sleep mode, very honestly, to make it very simple, the best way is to switch the device off, because we cannot rely on PSM, we cannot rely on eDRX, because we don't know how especially if the device is moving, in case if it's not a fixed device. So we don't know how the device may work in the field. So better to switch it off to save the energy. That's all for me. Thank you.
All right, thank you so much, Imad. And I guess we can fill up a whole webinar with just talking about the module and the network configurations and the optimizations. But I think for now, what's most interesting is actually to hear Dan's story, because you yourself implemented this module into your Walter module. So we'd love to hear more, Dan.
Yeah, exactly. So we're taking this theory and we're putting it into the real world. So and that's what we do. Let me tell you a bit more about who we are at DPTechnics. We do custom IoT, and we also do building blocks. So with the custom designs, we do PCB design, the embedded software, the cloud, UI, UX, everything that comes with an IoT project. We do that in-house, and we help our customers with their IoT projects. But we also have what we call building blocks. Can be both software or hardware. With software, we have our Blue Cherry platform, which has some crucial elements to bring an energy harvesting project to life. And we have our building blocks. We have Linux sums, but we also have the Walter module, which is the module that we're going to zoom in, which is used for the use case that we're going to discuss here. So let's go to the next slide and look at the Walter module, which I'm holding here, into detail. So onto the Walter module, you find the Sequans modem. As Imad said, it's a Monarch 2 chipset, and it gives you LTE Cat M1 or narrowband IoT. These are two cellular techniques which are in the LP1 category, so low bandwidth and long range, but also low power. You also have non-concurrent GNSS, so the same radio, base radio used for the cellular is also used for GNSS. This makes it also really low power. It's not for continuous tracking, but it's ideal to know where your assets are if you want to do some tracking applications with energy harvesting. And the module is fully certified with CE, FCC, IC, RCM. So Walter is really a building block that you can use to build your custom IoT products without going through the full certification hassle. Only EMC and spurious emissions is enough if you don't put an intentional radiator on your custom carrier board. Now, besides all these technologies, we also have the ESP32S3 as the main application processor. And this application processor is interesting for energy harvesting because it has, of course, the ultra low power coprocessor. It has quite an energy efficient deep sleep mode, which also the Sequans has. And this gives a total module power consumption in deep sleep of only 9.5 microamps. And I'm going to zoom on that later, but the deep sleep consumption is really important for an energy harvesting use case. Also, we have a software controllable 3.3 volt out, which is important because that means that you can power gate your peripherals, even if you connect peripherals which are not equipped with a power saving mode. And we have a really capable CPU so that you can use edge AI or any edge processing capability so that you don't need to transmit huge amounts of data to the cloud, which is, of course, an energy intensive process. So now that you know what the Walter module is capable of, let's zoom in on the use case that we're going to discuss today. So we are going to look into a use case that we have built for a customer that is already in the market for a few years, but that since last year we have converted to an energy harvesting use case with cellular, and it's currently successfully rolled out in both Europe and the United States. And that use case is bird protection for both horses and cows. Now, how's that done? What are the conditions that we need to meet or the targets that we need to meet for our client? Well, the birth prediction algorithm works by measuring the temperature of the horse or cow every 5 minutes. And based on that temperature graph, if we let the algorithm look at that graph, as soon as the temperature drops for more than 0.4 degrees, then we know that the horse or the cow is going to give birth within about 1 to 1.5 hours. Now, that's quite a difficult use case because we need to upload every 5 minutes to the cloud. You could say, okay, you can do more edge processing, but you want to actually upload to the cloud to know if your device is still in range of the cellular network. So we actually want to do an upload every 5 minutes. And also about 1 to 2 weeks before the horse is going to give birth, it's typically moved from outside to inside a stable, which is a really low light condition. So that's another difficulty in an energy harvesting scenario where we are, in this case, going to use light as our energy source. In the last 14 days of this application, the light is taken away. So that's an extra challenge. And also, this client, in the past, we had built a system on LoRa. So they had a difficulty that for the US and the EU, they had different SKUs, which was more a logistics problem. With the cellular, they really had the target of having a single SKU, which is perfectly possible with cellular because we are not in ISM bands, and with the Monarch 2 and with Walter, you can have a single SKU for global connectivity. So let's zoom in on the different hardware components that we need in this energy harvesting system. So we start by something that generates the energy. And that's in this case, a solar panel. So we have chosen for a solar panel, which is really efficient, almost 25%. And it's a solar panel from Voltaic. It's really small. So I have the sensor here. You can see it. It's about the size of my hand. This is already quite big. That again, because of the use case where the horse is maybe a few hours only outside, or also the horse is, this monitor is typically used between February and May, June, where the light is not not optimal. So we really needed to overpower the energy source, but still with this 2.5 watt panel, we can do really a lot. Then the PMIC, which is the heart of the energy harvesting system. The PMIC is the chip that gets the energy source and connects it to the battery on one side and also the consumers on the other side. So it is a battery charger. It is also a voltage monitor. And with the newer front end that we've chosen from EPs, we can also digitally connect to the PMIC and request different values like solar voltage, like battery voltage, and so on from the PMIC directly, which was a huge plus in this project. And then we have the application, which of course runs on the Walter module. So if we now zoom in how that looks as a whole, that's on the next slide. Then we see how that system looks as a finished product. So we have the energy source, we have the PMIC, and then we have, of course, the storage element. Here we have chosen a really special storage element. It's configurable in the production process. Either we choose hybrid capacitors, or now we choose sodium batteries. Why have we chosen sodium batteries and not lithium batteries? It is, again, because the system is used in the beginning of the year, and the system is typically placed on top of the horse. So it can be that at some point in time, it's still lightly or mildly freezing outside. And in comparison to when you build a system with a primary cell that is not charging, then you can get away with mildly freezing temperatures. But with lithium secondary cells, which are charging, you cannot charge a lithium cell below 0 degrees Celsius, because then there are dendrites forming inside the cell and you will get damage. But with sodium batteries, you are allowed to charge with sub-zero temperatures, which is a huge plus. Also, again, because the company wants to send the sensor with the batteries inside, because there is no lithium inside, it's much more easy to send the sensor worldwide. So the natrium or the sodium batteries are a huge plus for these two reasons. The MCU is the Walter module, and the protocol, and that's really important. That's why what I was talking about in the Blue Cherry platform, we use a CBOR over CoAP, because there are two things important in energy harvesting. It's looking at the sleep current of your sensor. You want to be really efficient there, because that's where most of the time your sensor is going to be. But also, when you are transmitting and processing data, you want to do this as efficiently as possible. And you can be quite naive and do an HTTP post. Setting up an HTTP post over cellular, you're going to negotiate a TLS session, which is going to be a few kilobytes of data, and then send a JSON body, for example, just to send a temperature, which is a huge overhead. That's not something you want to do in an energy harvesting use case. That's why in the Blue Cherry platform, we support real translation of data and the CoAP plus DTLS transport with connection IDs. So we set up a secure session one time over CoAP plus DTLS, which is a UDP-based transport. So the first time we are consuming a bit of extra energy and data, but each subsequent data transmission, we are only using a few bytes in CBOR to send the raw temperature, which is a huge saving of energy. So if we now look at what that means in worst case scenario, so really bad signal condition, no lighting, then we still get a really, really long use of the sodium batteries, and with a lot of flattenings of the curve. So if we would look at the battery voltage in the outside world, it would not be an interesting graph, but because we are almost between 100% and 99%, so I didn't include it here. But this is a graph when the sensor was actually in an almost dark stable with only some light from high up windows. And then you see that in the night, we sometimes get some drops. When the signal is really bad, then the modem transmit power goes up to 23 dBm, and we get some retransmissions, what Emmet was talking about. So then you see that the sensor, that battery voltage drops a bit more. But overall, you get a lot of flat spaces in the graph, which is where, even with this really low lighting condition, the energy harvesting is doing its job. So let's go to the next slide and see how that looks on the PCB. So I have it here in my hand, so you can see how that looks in the real world in size. So you get only two 18650 batteries, which are just standard batteries, but the sodium variant. Outdoor, we stay between 90 to 100% state of charge anywhere. We tested here in Belgium, we tested in the US, we tested in Norway. So good weather, bad weather, you don't need full sunlight to do this heavy energy harvesting use case. And we have, because of the newer EP's chip, a full energy awareness because of the I2C front end, and we can talk directly. We don't need to rely on external ADCs to know what's going on with the battery state of charge. So that's it on my part, and I'm more than happy to now deep dive into technical part of the PMIC.
Thank you so much, Dan. I'm going to zoom in on your video. So can you show it to us one more time, a bit more slowly, so we can actually look at what it is like in real life? Okay, and then the other side is the solar cell.
Exactly.
The solar panel, okay.
Yes, and in comparison, this is the size of my hand. So it's really not that big, and it goes on top of the horse. And then we have the temperature probe for the body temperature.
Yeah, exactly. Yeah. Awesome. I'm sure there are plenty of questions coming in by only looking at this this design that you make. So it's really exciting. But before we dive into those questions, I would love to give the floor to Bruno, who is explaining what this actually means and how this actually works, this whole energy harvesting module.
Thank you, Lawrence. Thank you, Dan, for the introduction of the use case, and to Imad for the explanation about the beauty of the chipsets of Sequans. So, in fact, what is interesting in what Dan and Imad have said together is that their application use case is combining different use situations, one where you are outdoor, one where you are indoor, one time where your application requires a lot of energy, one moment where it is requiring less energy. And to solve these typical situations of combinations, we wanted to introduce a new PMIC that is shown in next slide. And this new PMIC is enabling to harvest up to almost 3 watts of power from whatever energy source, and also be very efficient, not only at very high power, but also at very low power. So this gives an idea that IoT is not just a matter of microwatts and tiny applications. It is extended to domains where the requirement for power and for energy are becoming wide. Not only cellular outdoor, you can also add GPS modules, all these things that were always attached to big battery packs, heavy battery packs. And now it's no longer the case. Why? Because not only we can find efficient cellular application chipsets, we can find smart implementation of application, and also quite beefy storage element and energy harvesters. And in between, you have a modest PMIC that is AEM15820 that has to play an important role, which is to convert this light energy efficiently from the solar panel, whatever size it is, to the storage element, whatever size it is. And similarly, once the energy is moved from one to the other, making sure that this precious energy is not dissipated as heat and used conveniently with the application. So that's why at EPs we have spent several time and a lot of focus on designing this new PMIC, which has, as you see here, a very high efficiency for converting energy. Moreover, there are some times where the device you manufacture or you create may be stored into a drawer or a location where it is spending energy doing nothing. So we had also to add some specific backup charger, a 5-volt charger, that in case of the device is lost for months or years somewhere in a drawer, you can restart it fast. And this is why we added this backup 5-volt charger that is listed here. We will get back to that a little later on. And obviously, key point of these energy harvesting modules, including everything, are the storage element. And since they are precious and quite big, they have to have also protection schemes that allow them to live and to live forever and to support the heavy duty of the application. So in the next few slides, I will show what we do for these different topics. Item 1, energy conversion efficiency from the source, the PV photovoltaic element, to the storage element. In each of those slides, I will highlight the specific block of the PMIC shown here in the center with respect to the output and the input of the energy source. We said, and Dan said before, that he has been selecting a 2.5 watt peak PV cell from voltaic systems. This means that under bright light, full sun at noon, solar noon, it can create about 2.5 watts. However, when cloudy times come, you have probably 1/10 of it. And when you are in the stable, you have 100 or 1,000 of it. And you have to make sure that whatever the lighting conditions are, your PMIC will be capable to give the maximum of this energy to the storage element or to the application. And this is exactly what we have focused on at EPIS for this product, AM15820, and is shown here on the right side of this slide. You can see that whatever the current of the source, 1 amp, we can imagine it's 1 amp at 1 full sun, down to 100 microamps, which is in the stable, you see that the efficiency of conversion of the PMIC is staying at around 95%, 90 to 95%, which is really giving you the best of worlds, whatever the situation is for the energy source. Now, if you go to next slide, you will see that similarly, we have to make sure that the energy that is stored in the storage element is preciously used to drive the application, to provide energy to the application. And you see from the bottom right slides that similarly, we have also very well focused on efficiency from storage element. Here it is a sodium-ion battery to the application. Whatever the storage element voltage is, from 2.8 volt up to 3.7 or even 4.3 volts, whatever the load, you see that the application efficiency side of the PMIC is about 95%. And all over, you get that your application does not burn energy doing just conversion, which is extremely important for enhancing and extending the storage element and application lifetime. Next one is in case of, as I said before, in next slide, you can see that we have also implemented a sort of fast charger system on board in the PMIC, which takes energy from a 5-volt typical USB power source and is capable to move this energy straight to the storage element. And you can see that whatever storage element you use, whether it is a sodium-ion battery or a lithium capacitor, you can very fast reach a situation where you can start your application. So imagine you have left your product for several months without seeing any light or in a drawer somewhere. You can see that you can rapidly, in 7 minutes and a half, get to a level where the application can start, which is quite convenient for instant start installation, or just to make sure that your application is ready to be used after being stored in somewhere in a place that is having no light. Obviously, it is clear that with capability of sodium-ion batteries today, if you put 1, 2, 3 sticks together, you have such amount of energy that you can survive for months, making sure that your application is working once forever. In the next slide, we show that those storage elements may be fragile. They may be fragile at use. So we have to make sure they are protected and have extremely long reliability time. And to do that, the PMIC itself has some properties, some mechanism to protect them. You can see here we illustrate the two cases that Dan has mentioned before. He wanted to be capable to support lithium-ion capacitors. So we do it natively just with these GPIO configurations, or it can be also using a sodium-ion battery alternative, and simply by configuring the GPIO pins, which are as simple as pull up, pull down on the PCB, you can configure to be compliant straight for sodium-ion batteries. Obviously, you can also support nickel metal hydride batteries and more. That's native from GPIO interface, but you see at the bottom, I had a mention that since this PMIC has also got an I2C bus embedded, it's quite easy to interact with the MCU and to set specific custom modes that you have because you have a specific battery or a specific use case. You can play with these things really from the MCU control level. In next slide, I show that there is also few added values to the PMIC. Previously, Dan has shown that the module layout is quite packed, and you see here the contribution of the PMIC, despite it is full featured. It is pretty dense and having a few square centimeters of area. This is the yellow box. All around this is the evaluation kit that I have nearby me with all configuration with GPIOs and the connector from either I2C directly on the extreme left side, or if you look at the top left, you have a USB connector that allows you to interface directly to the PC. So small footprint, ready to use layout. That's one value proposition of this design. Additionally, complementary bill of material is multi-sourced, so you can select passive components, coils from multiple vendors. You can select also storage elements from multiple vendors. That's really an open box. We have also a nice evaluation kit that you can see here with USB connector and a PC application. And I can show it to you, this setup I have here, and we will go to a sort of live demo. So I have put here together my setup with a smaller PV than Dan is using, but still a 300 milliwatt PV cell, a single sodium-ion battery with thermal control and thermal monitoring. And my application is less complex than IMAD ones. It's a simple resistor that is drawing continuous current. So this is my setup, and I invite you to look at this screen capture that I will share now, which is a real-time work of the PC interface. So you see my setup. I have a command register here where I can write and read the values I want to give to the PMIC to work and to override the GPIO setups. You see here that the low power situation is running from the PV cell. I am indoor in the shade, so I am harvesting half a milliwatt here. I have been working for 20 minutes, and I have already collected 1.8, 1.9 joule. And in parallel of that, I see my application, which is my small resistor that I am putting here, is collecting energy from the whole setup. It's about 40 milliwatts average. So you see that it is unbalanced. I produce less energy than I do use. But if I open the window and get the sun shining, let the sunshine in, like I said before, you see that immediately my high power section starts to work. And here you see that I am collecting already about 50 milliwatts. The sun is moving a little outside, but you see that I am harvesting much more, and I can really yet compensate by the sum of both. I can compensate the power that my application is using. So now I am charging my storage element, as shown here, and I can also monitor my temperature, which is the temperature on the storage element. And it looks like, by the way, I have a misconnect. Yes, good, good. You can see that I have quite hot weather here with my storage element that is now running at about 31 Celsius. And I can obviously stop it from charging and discharging when the temperature is going out of range. So that was the little demo I wanted to show you. And with this demo, I transmit the link to Lawrence. Thank you.
All right, thank you so much. That was really cool to see. So it's live, and just to validate, the data we saw was from that kit that you showed in front of the camera, correct?
Yes, I'm going to close my window because it is getting in. Yes, this is exactly what we offer from our website. You get the EVK, that is a little piece in green here. Free of charge graphical interface you can download from the web. And then after, it's up to you to connect whatever ecosystem around, either a 3-watt PV cell like Dan is using or a smaller one. There are plenty of options, plenty of partners that are doing such things. And on the storage element side, similarly, you can do whatever you like. Lithium capacitor, sodium ion, lithium batteries, nickel metal hydride. It's really open and programmable.
Super exciting. Okay, I saw some questions coming in, so we'll dive into that. But first, how do I get started myself? Dan or Bruno, would you like to share?
Yeah. Okay, from our side, it's really easy. Either you buy a loose Walter module and some antennas, and you go to our GitHub, download the Walter modem library. You can program in ESP-IDF, Arduino, MicroPython, or Zephyr is supported. And then you connect it up to the EP's development kit, Bruno.
Yes, so on the same marketplace like shown, Mouser, you can get also the EVK of AM15820. You can get this EVK, you can have brochures, everything that is needed. You do not hesitate to contact us, to contact EPs, to connect with our application engineers. We are really happy to support you. And if you need more information about how to connect storage element and PV cell, you may go directly to Voltaic System website or ask us for advice.
Same on our side. We are really open to support. We have, of course, our email support. We're open to GitHub issues. But we also have on the quickspot.io website, you find the link to our Discord community where almost 500 engineers are always available. And also our full engineering team is available on the Discord. So you have direct one-on-one support with one of our engineers to ask anything about the cellular connectivity, but also about the energy harvesting. We're more than happy to help.
Okay, amazing. Well, I'm gonna try to give a short conclusion, a takeaway, the things that we discussed here, and it's been a lot of information. But at least for me personally, you don't need to understand how everything works to make use of it. And the good thing is that Sequans and EPs and DPTechnics, they did all of the technical work. all the pre-certification, so you can basically just implement and bring the tools together. And it brings me mostly to the first point that it's, I don't know, it's here, and we saw like a real demo from Bruno. We saw that there's actually DPTechnics is shipping products in the market, so it's actually there. And I think what Imad showed us that it's not just about energy harvesting, it's not just about optimizing the energy performance, but they really go in tango. So like the one comes with the other, and just optimizing your connectivity or your communication module is not enough. So you really need to tie it in to one another. Real world deployments are demanding. It works. It may work very nicely on paper until the horse goes indoors, and then your whole use case may go down the drain. So real world deployments are challenging. So keep that in mind, do lots of testing. And it's all about power. That is the #1 constraint. We can talk about the bill of materials and the build the tools, but as long like the moment your device is out of battery, then I don't know, like the cost involved to manage that's beyond any device or any operation. So power is really the #1 constraint. Well, the ecosystem wins. I know I fully agree there. Like, don't try to reinvent the wheel. Pick and choose your partners and try to implement everyone, all the services they provide. And the cool thing is, you can build it today. You can start today with one of these dev kits. And then the first question from my end, everything sounds fun and games until you have to draw your wallet. So, Dan, can you give us some highlights about what would it cost to actually start using your products?
Yes. So with Walter, that's really straightforward. In single quantities, and Walter is really made to also allow companies that don't have the huge volumes that are typically needed to do something custom. You can start with Walter in a single unit, the quantity, and then it costs about 59 euros for a module. And it goes up in volume, and then you can, if you buy like 500 Walter modules, then you're already at 20% off. So it of course goes down in volume, but you don't need to have the huge volumes in order to make something custom. And for the Blue Cherry platform, where you get the low power optimized protocols, where you get OTA updates, CRA compatibility, and so on and so on. You can even run your application in the cloud. That's all, you get an all or nothing. So it's really transparent. It's 50 euros a month for 50 devices. And it's 250 euro a month when you go up to 1,000 devices. So really transparent on pricing there.
Okay, same question to you. Would you like to share what the PMIC and the evaluation board and how to get started? Like what do I need to think of?
Yes, so really the evaluation board is available on Mouser. You can see the price. It's about 100 euro or so, but it's really not the price of implementing, not the cost of implementing energy harvesting into the field. Reality is much lower than that. We have mass deployment of products into end product like remote control units, which are very, very cheap, below the $10 level. Moreover, I would like to add the important point is about energy harvesting is a lesson about total cost of ownership reduction. If you implement same solution as Dan explained, powered by disposable batteries, you would have to continuously monitor the battery level of your application, go to the horse wherever it is, remove the pack, open the box, replace the battery, move them away to the garbage, and make it sure they are recycled properly. And that's costing a lot in a B2B application. Medics and the people who are taking care of horse, they don't want to ride and go after their animals and remove the sink, remove the belt, hurt them, and make the maintenance with standard battery packs. It's really a value proposition that energy harvesting is bringing, giving better quality of service, very important in cellular, by the way. Maintenance-free systems and total cost of ownership that is reduced significantly.
Yeah, clear. Thanks, Bruno. Okay, on to the questions. We have a few minutes. I'm not sure if we're gonna have time to address all of them. First, something to clarify, Imad, there's also something about ambient IoT and 3GPP release 19. That's something different, right? Maybe enlighten us.
Absolutely. I mean, the ambient IoT is the term is part of the release 19, which is a 6G coming later. Indeed, this technology or this feature or whatever requires a full webinar by its own. Once it's, we can address it in a full webinar dedicated to it. The good thing about having this ambient IoT in 6G is the proof that what we have been discussing today is somehow the trend or everybody is moving or there is a need to move to a deploy and forget kind of applications. But again, what we have been discussing today is really based on our existing technologies, 4G or 5G today, and we're not exposing what is coming in the 6G release 19.
Yeah, okay, clear. Thanks. Bruno, you've only been talking about solar energy, but there are also other types of energy sources like thermoelectric generator.
Yes, definitely. That's something we could even think for powering the use case of Dan, because the animal can be having a quite high body temperature, and the outside maybe, as he was saying, freezing. So you have certainly here something to explore, which is using thermoelectric generation for powering mobile IoT, ambient IoT. There are solutions for that. There are sensors for that. Typically, the same product as we showed before, 15820, is capable to handle TEG generator, thermoelectric generators. It would be an interesting use case to dig in. Obviously, other applications like smart home valves, thermoelectric valves, and so on are a no-brainer. But the case of Dan may be also to be explored.
Okay, so you change the sensor, or at least the energy harvesting, but yes, the power management
the PMIC must
stays
be
the same.
Yes, it's just to connect the energy source, the alternative energy source, possibly reconfigure a bit the GPIOs or via the I2C to make sure it fits with the property of the TEG. Each energy harvesting source has some peculiarities that needs to be understood and managed by the PMIC. But once it's done on the source, don't change anything on the application, don't change anything on the storage element, it's managed the same way.
Yeah, okay, thanks. Clear. Dan, let's see. So you've been using sodium batteries. What are other advantages of sodium batteries in comparison to lithium batteries or supercaps, and when to use which?
Yeah, so we first designed or were looking at the storage elements for this specific use case. They needed to be relatively compact, and at the same time, we needed to have them be able to be used only a small portion of the time, so between May until the end of June. So that meant that also the self-discharge need to be either low, or the storage element needed to be capable of being able to be depleted without the storage element breaking. And also it needs to be able to charge in negative temperatures. So lithium was quite difficult because it needs to be maintained at quite a high voltage in order not to break. You cannot charge it at under sub-zero temperatures. And also it's difficult to ship. So with sodium batteries, it's also an interesting thing about sodium is that we can charge it to quite a high voltage, also almost 4.6 volts, which is higher than a normal lithium battery. And because we don't have a boost converter on the board, that means that we can have a more usable portion of the voltage swing of the complete storage element for the modem. Also, we can have a sodium battery be depleted to almost 1.0 volts without any degradation of the storage element. So when people don't charge the solution here and they put it inside a drawer for 8 months, then the chances of the storage element being broken are really, really low. Also, because there are no lithium elements in the batteries, it's not a problem to ship. And we are working with animals which can damage the sensor if they are really harsh. You know, you can puncture these cells, you can break them in two, nothing will happen. With a lithium cell, you should try it. Some things will happen with a lithium cell, which is not the case with the sodium. So these are really quite some advantages that we see in comparison to lithium.
So it's
a downside, maybe if you really want to make a really small device, the energy density is a bit less, but it's okay for this use case.
Yeah. Okay. Thanks. We're running out of time, so let's see. I want to have one final question. Imad, I give you 30 seconds to answer this. Can LTE-M and Narrowband IoT operate on a 5G cellular network? How does that work?
I'll do my best to answering to this question in 30 seconds. However, I mean, and quickly to say it, despite the fact that the LTE-M and Narrowband IoT have different waveform compared to the 5G, but they are considered as part of the 5G since they are part of the release 15. Now, I mean, basically speaking, when we discuss with most of the operators, despite they are decommissioning the legacy 4G between now and sometimes in the coming years, the LTE-M is somehow here to stay for years because there are many smart meters which are deployed in the market using this technology, and the smart meters require at least 1 decade of operational existence. So meaning between, I mean, the number that we see today that LTE-M is here to stay to 2040 most of the time, no matter, I mean, independently how the operator is going to manage this coexistence between LTE-M and the 5G core network and etc. I mean, all the technical things behind, but it's here to stay for a long time. So yes, it is part of the current deployment, even when let's say RedCap and eRedCap are broadly available in the market. LTE-M would stay here for a long time. Yeah,
it will be there to stay. Okay.
Yeah.
Thank you so much. I know we've not covered all the questions, but just ping us on email or find us on LinkedIn and ask your questions there to the speakers directly. That being said, thank you so much for all the speakers. Thank you so much for joining in this long. I think it was a lot of fun. And yeah, we'll keep an eye on your email. We'll send the recording as well as the link to get your hands on the dev kits yourself. Thank you so much.
Thank you. Bye-bye.
Thank
Thank you all for attending.
Bye.
Bye-bye.
Bye.